this video, let's work on some examples to illustrate how to determine the complete response of RC and RL circuits. In this example, we have a switch that can select between points A and B. The problem states that the switch has been in position A for a long time, and therefore we can say that the circuit is in a steady state. And then at time t equals 0, that switch transfers to position B. Here we are asked to determine what is the voltage across the capacitor for t greater than 0, meaning the voltage after the switch is transferred to B. And then we are also required to know what is that voltage at t equals 1 and 4 seconds after the switch is transferred. For B, we are required to plot for the voltage of the capacitor before and after the switch is transferred. For C, we're required to determine the steady state value of the voltage after the switch moves to B, and how long will that steady state value be attained from the time the switch transfers to B. And lastly, we are to determine the voltage across the resistor 4 kilo ohms as a function of time after the switch moves to B. Here is our circuit from the time the switch is transferred to B. So it is a series RC circuit where we have indicated the current, the direction, and the voltage across the resistance V sub R. Since this is a series RC, we can use the equation that we have derived for a series RC circuit. So this is the equation where V sub S is 30 volts, RC is 2 seconds, V sub naught is the voltage across the capacitor at time t equals 0, and that voltage should be equal to the voltage of the capacitor prior to the transfer of that switch, written in this manner. How do we get the voltage before the switch transfers to B? Well, we have to look at the as part of the circuit before the switch transferred. So that part of the circuit involving the capacitor is this circuit. So this is 5 kilo ohms, this is 3 kilo ohms, and the capacitor is drawn as an open circuit, indicating that the circuit is at steady state, where this voltage here is equals to the voltage across the 5K, and we can compute that using voltage divider. So that is, so let me write it here. So V is 24 times 5 plus 3, okay? So this should give you 15 volts. So this one should be 15 volts. Now that we have the initial voltage of the capacitor, we can proceed in using this. So plugging the values here, we will get this, and finally the equation for the voltage across the capacitor. So take note that this equation is applicable for time between 0 and infinity. Now that we have the equation for the voltage across the capacitor, we can get that voltage at t equals 1 and 4 seconds, and that should give us these values. We can also plot that voltage before and after the switch is transferred. So before the transfer, the voltage is a constant because the circuit is at steady state, and then the switch is transferred at time t equals 0. The voltage undergoes a transient condition, so it changes from 15 volts uh, and goes up to 30 volts, where it stays there as its new steady state value. We also observe that the voltage is increasing fast initially, and that rate of increase slowly decreases as time increases. So the new steady state for the voltage across the capacitor is 30 volts, so it is written as V at time infinity. To get to that voltage requires approximately 5 RC if the capacitor has no initial voltage. So this is about 93.3% of the charging voltage V sub S. However, since our capacitor has no initial voltage, that time should be lesser. And to compute for that time, we can use this equation. So we let the value of V as 93.3% of the charging voltage, which is 30 volts. And then we equate this with this one and solve for the time. So we will get there around 8.54 seconds, which is actually less than 5 RC, which is 10 seconds. We can make a double check by computing for the voltage at 8.54 seconds, and that should give us this value, which is very near to the steady state of 30 volts. Given the equation for the voltage of the capacitor, we can also find the current through that capacitor, which is also our current through the circuit. Take note that the current is drawn as coming out from the positive terminal of the source. So we can use this relationship, and since we already know V, we can get the derivative, and that should give us a current that is like this. From there, we can also compute for the voltage across the resistance using Ohm's law, and that should give us this answer. So the voltage across the resistance is a decaying voltage and will vanish over time. This example is a continuation of example 1. So after the switch is transferred to position B and the circuit attains a steady state condition, we transfer back the switch to A. Then the question is, what is the voltage across the capacitor after that switch is returned to position A, and also the current through the 3K ohm resistance after the switch is transferred. So this is the current, and the steady state values of the voltage and the current mentioned in A and B after the switch is returned to A. Take note that the circuit is in steady state before the switch is transferred back to B, because the problem stated that um, that switch is transferred 20 seconds after uh, it moves to B. So that is enough time for the circuit to attain a steady state prior to the transfer of the switch back to A. So that means that the initial voltage of the capacitor when transferred to A must be equals to 30 volts. Also take note that we have moved T equals 0 as the time when the switch is transferred back to A. So to solve for V, uh, we notice that the circuit is not a series RL or series RC circuit uh, where we can apply the formula for the voltage across the capacitor. But we can take a look at this part of the circuit and we can replace that by its Thevenin's equivalent. So to do that, we isolate that part of the circuit and determine the Thevenin's voltage and resistance. So we'll get 15 volts here by doing a voltage divider across the 5 kilo ohm resistance. For the Thevenin's resistance, after shorting the source across the terminals, the 3 and 5 case will be in parallel, and that should give us this result. Then we can redraw the circuit using this circuit. So the circuit on the left becomes this one. Now, this is a series RC circuit, and we should be able to use the formula that we have derived. Okay, so after converting the circuit into a series RC, we use the formula. Uh, we know V naught to be 30 volts, so plugging in the rest of the values, that should give us an equation for V that is like this. And take note that um, this voltage is good for T between 0 and infinity, where again T equals 0 is the time when we transfer the switch back to A. Also note that I have computed for the new steady state voltage of the capacitor, and that should give me 15. So by letting T here equals infinity, I should be able to get the new steady state of the capacitor voltage. Then we go back to the original circuit uh, where we already know the capacitor voltage V as this one. We can perform a KVL to get the current around this loop. Okay, starting from here, that should give us a KVL equation that looks like this. Okay, so we use the voltage across the capacitor in writing the KVL equation. Solving for I, that should give us this expression for the current I. We could also get the steady state value of I, and that should give us 3 milliamps. Now we can plot the overall behavior of the voltage of the capacitor from the time the switch is in position A, then it transfers to B, then 20 seconds after it is transferred back to A. So for a T or before the switch moves to B, This is the behavior of V, so it is a steady state at the value of 15 volts. Then we transfer to position B. It undergoes a transient and then settles to 30 volts. And 20 seconds after, we switch back to A, and that should give us this curve here. So this point here is actually 20 seconds after the switch is transferred to B, but we have reset the time t equals zero for this example as the time when the switch is turned back to A, and that should give us this curve here. So as we can observe that A starts, or the voltage starts at 15 volts, then it increases to 30 volts, but eventually returns back to where it uh, began, which is 15 volts. In this example, we have an RL circuit where the switch has been closed for a long time. So we are required to determine the current through the inductor and the voltage across the inductor with the indicated polarity. So this is the circuit at t equals 0, or after the switch is open. To determine I, we cannot use the formula for the series RL because the circuit is not a series RL. But we can do source transformation to convert this part into a voltage source. So that should give us a circuit that should look like this if we are to convert that. So here it should be 10 ohms, while this one should be 90 volts. We can combine 10 and 5, and that should give us a circuit that looks like this, which is now a pure series RL. So this should be 15 ohms and this should be 90 volts. Now we can apply the equation for uh, the series RL. So using this circuit, we now compute for the current. So this is the current here. So the current should be um, Vs over R plus the initial current, Vs over R, e to the minus R over Lt. Okay, so Vs there should be 90 volts. Well, R should be 15 ohms and L is 1.5 henries. But what is I naught? So that is the initial current through the inductor before the switch is open. So we go back to the circuit before the switch is open. So this is the circuit. So this is I think 5 ohms and the switch is closed. Okay, this is 10 ohms and this is 9 amperes. Now this is at steady state, so therefore the inductor is a short circuit, and that would mean that if we could ignore the 5 ohms as well as the 10 ohms. So that means the current here at steady state, which is our I now should be equals to 9 amperes. Okay, so this thing here should be equals to 9 amperes. So now that we have the complete data, we could now solve for I as equals to uh, 90 over 15 ohms plus, so this is 9 here minus 90 over 15 should be e to the minus 15, and this is 1.5 here, and that should give us I, and that should give us I equals 6 plus 3 e to the minus 10t. Okay, so this should be our equation for the current. Now for the voltage across the inductor, that should be L di dt, and that should give us 1.5 times the derivative of this current, which is minus 30 e to the minus 10 t. Okay, so minus 30 is 3 times negative 10, and this should be negative 45 e to the minus 10t. Okay, so this should be our um, P sub L. So it's a negative voltage. So meaning the polarity of VL here should be, this is positive and this is negative.